My co-presenter here is Brooke Wenig. You might recognize her from her awesome demo at the keynote this morning, but for those who missed it, she is a machine learning practice engineer over at Databricks, and she's been working there for the past 3 years or so.
And we want to give special thanks to Amir Asai from Databricks for his contribution to the work in the slides, as well as Kevin and Aaron up front from FIS Global.
So let's get started. So first, we're just going to give you a quick outline of what we're going to talk about today. So first, we're just going to give an intro to who FIS Global is and who Databricks is. Then we're going to outline our business problem and what the motivation was for working on this project. Then we have a couple different data science approaches that we tried out. And finally, how we took that to production. So who is FIS Global? FIS Global is a global leader in financial services. We're one of the largest fintech companies in the world. And our clients are largely smaller banks and credit unions. We provide these clients a vast ecosystem of different financial services, largely mobile banking, online banking, and hundreds of other services such as payment services and wealth management. So particularly my team at FIS Global, we're the data team. We take all of the data that these services produce, we process it, and then we dig into it to deliver insights both internally and to our clients.
So who is Databricks? Hopefully you guys all know you guys are at the Spark and AI Summit. We were founded by the original creators of Apache Spark.
So let's get right into it. We have our business problem. We're just going to outline our business problem, but first we want to just give you a little bit of context on the problem we are solving. So largely the problem that we were working on was one of conversational analytics. And so I just want to give a little bit of insight on what we mean by conversational analytics. And I'm going to start by saying what conversational analytics isn't. So conversational analytics isn't just simple call center metrics. If you're working at a call center or if you're doing analytics at a call center, largely the types of metrics you're looking at traditionally is just how many calls are happening, how many calls is each person making, how long are these calls lasting, and maybe a success rate depending on what you're doing at your call center. So really these metrics are about measuring the effectiveness of these call centers. When we're talking about conversational analytics, we really mean how do we dig into the text of the conversation and really get deep insights onto what's happening in these conversations. And really we're talking about measuring quality of these conversations rather than just simply the effectiveness of them. So we want to be able to, one, measure how happy our users are in our support conversations, and we want to be able to follow up on some of the conversations that maybe didn't go quite as well as we had planned. I know we've all probably experienced some of those. So really, you can see that conversational analytics is taking these call center metrics to the next level and really getting to our pursuit of happiness. So just to give a concrete example of what we're going to be looking at, we're mostly going to be looking at support chat. So we'll have a user talking to an agent. Here it says they lost my access card. Here in our case, it might be, oh, I lost my debit card. Could you please cancel it for me? And the agent at the other end, whether it's a human or a support bot, will be able to do that for the client. So that's all great. We know what conversational analytics is, but why does FIS care? If you ask any bank executive or a banker what the core business of, or what really staples a bank is, it's about a relationship of trust. You got to trust that bank with your money. And really, that trust is built on communication. And so before mobile apps and online banking, these conversations were happening face-to-face in the branch with your banker or your teller. Nowadays, we've moved on from that. We have some mobile banking apps and online banking, and we need support channels for those. And those have been opening up new conversational channels. We also developed, support chatbots that can maybe automate some of these processes where a human might not be needed. And most recently in banking, we're seeing a lot of interest in conversational banking. Conversational banking is where you might be talking to your smart home device, such as Alexa, and say, like, hey, Alexa, let me check my balance, or hey, Alexa, transfer money to John. So really, we're seeing a development of all of these new conversational channels, and all of these new conversational channels are opening a bunch of new use cases for conversational analytics. The main difference between these newer conversational channels is that we're producing a lot more data. We have all of the conversation data for the support chat, and we want to be able to dig into it so that we can increase the quality of our support and maybe remove any pain points that are happening in conversations. Alongside of this, we've also been advancing our data processing capabilities. So we can scale to huge amounts of data that we need to. Like we said, we support thousands of clients, and we have our solutions running on millions of different devices. That creates a huge velocity and volume of data that we need to be able to process, and we've also been advancing in our analytics capabilities to be able to dig into these conversations. So the new data and the new processing capabilities really enables conversational analytics. And since banks are really reliant on these conversations, you can see how banks have a necessity to dig into these conversations and be able to make sure they're going as well as they possibly can. So we had to set up some goals for the project that we set out on with Databricks. The first goal that we had was that we needed to be able to measure the overall sentiment. We want to know, did that conversation go well? Was it kind of hit or miss, neutral, or did it go bad? Next, we wanted to be able to know what exactly contributed to the success or the failure of that conversation. And we wanted to be able to analyze what was going on. The key to that is going to be AI and natural language processing, as you might have guessed from the title of our talk. And then finally, we need to be able to do this at scale. So to that, we turn to Spark, and we turn to Databricks.
All right. Oh, sorry. Thank you. So now I'm going to walk you through the two approaches that I took to this problem. As you can probably tell, approach V1 did not go all that well, but let me show you what I did so you don't repeat the same mistakes. So as a data scientist, I wanted to see what open source libraries there were out there that I could use for sentiment analysis. And so I had found some of these key ones. First one is NLTK, Python library. Next one is TextBlob, another Python library. Then John Snow, not that John Snow, John Snow Labs. And Stanford CoreNLP. And so John Snow Labs, it's a third-party library that integrates very well with Spark. So it does distributed natural language processing, and it has both Python and Scala APIs, which is what made it really nice. And Stanford CoreNLP, it's written in Java, but it has a Scala wrapper, which we can then use in Spark. So how did these libraries do? So this is my input text. Thank you for resolving my problem. TextBlob had said, hey, that has polarity 0, subjectivity 0, pretty neutral. But then NLTK had said, that's a little bit negative, perhaps because of that word problem, a little bit positive. Overall, it's a positive sentiment. Spark NLP, also called John Snow Labs, that just said that was a negative sentiment, whereas you and I know that's actually not a negative sentiment at all. And Stanford CoreNLP also erred on kind of the negative side. And you can see one of the problems here is actually all of these libraries use very different scales. TextBlob ranges from -1 to 1. NLTK has the same range, but you can see different values for them. John Snow Labs simply will tell me negative or positive, and Stanford CoreNLP has its own rating system altogether. So no better way to show you this than with a live demo. And for that, I would actually like to get an audience member to volunteer a politically correct statement about this conference. You can see my previous ones. Thank you for resolving my problem. Yes?
The keynote speech was awesome.
Keynote speech was awesome. All right. And so here I have this notebook that I created called define user-defined functions. This will take my text blob code and my NLTK code and create a Spark UDF. Oh, sorry, I don't know why it's not. How do I get it to switch displays? Drop out of here. Oops, end show. OK, sorry, thank you. So here I have a helper method, which defines my user-defined functions inside of another notebook that I can run them here. So it creates a user-defined function for my NLTK, my text blob, and then it just imports John Snow Labs and Stanford CoreNLP. Here, I'm going to create a Databricks widget where I can input my input text here. I can't spell awesome. And then I can go ahead and get that value and create a Spark data frame. So notably, the Spark data frame only contains one record, which is this input text. And so because we're using Spark, we can easily switch between languages. So even though I did this using Python here, I can now make my predictions in Scala down below, get that value, and see what it says for the different libraries. So TextBlob, it said this is actually a very positive sentence. NLTK, no negativity, but still not full positive marks. Spark NLP, we got positive. CoreNLP, for whatever reason, it still keeps saying 1. And so I want to go ahead and increase the positivity. Let me add 4 exclamation points. Let's see what the model says. 1, 1. OK, NLTK suddenly just gave us neutral, actually. Spark NLP, we're still positive. CoreNLP is not budging. All right. So these are some problems we encountered with that first approach. We were trying to do turn-by-turn level predictions with these open source NLP libraries. But Stanford CoreNLP actually gives predictions per sentence, not per turn. So if the user had 3 sentences before the agent responded, it would only give a prediction for the first sentence. And then I didn't want to average them out together because it could be like, hello is the first sentence. My name is blah. And so that was one of the issues we'd hit, was predictions per sentence, not per turn, with Stanford CoreNLP. The other one is it did actually very poorly with neutral sentences. In general, it's pretty hard to get labeled examples of neutral sentences. And you think about it with Yelp, Netflix, et cetera. When people rate things, they either love them or they hate them. It's very rare to see people rating restaurants with 3 stars. Most stars are actually 5 or 1, not 3. And in fact, John Snow Labs actually has no neutral category. And it did not do well with the banking domain at all. And so now our billion-dollar question is, can we do better? So this is approach v2. So with approach v2, there are no pre-trained sentiment analysis models. We use that kind of as our benchmark to see how did they work. But in general, they were pretty rigid and rule-based approaches. They would try to text match certain words like problem, for example, or awesome, and assign some weight to them, which didn't generalize very well. So we got rid of that. And then this is our new model. We actually built an LSTM, long short-term memory, model on all conversational text to predict the sentiment. And this one, we actually used all of the text from both the user and the agent to predict the sentiment. We did benchmark it with just the user text, found it gave us slightly better results to actually include the agent, because some of the conversations had human support on the other side. And so we wanted to know also if the agent was having a bad day. Then we augmented it with some additional features. For example, the number of terms, the time of day. Because if a conversation only has 3 turns, odds are they probably didn't resolve your problem. Or if you had 100 turns, odds are it took a very long time to resolve your problem. So we included some additional features, which we'll talk about more on the next slide. Then we passed the LSTM output along with those additional features through our end classifier. And lastly, we actually simplified our problem to just predict positive or negative. We got rid of the neutral category. It was actually proving too difficult. And so we wanted to just know positive, negative. Having the neutral category actually didn't really impact our follow-up, but having neutral didn't really impact our end follow-up, but having negative certainly did. And so I'm going to walk you through the steps that we had used to build this LSTM and then our overall model. So what we did is we found an open source data set with some labeled examples. Our internal label data was quite small. We had lots of data, but not a lot of it was labeled. And so we had found an open source data set and did distributed training of the LSTM on that open source data set. It wasn't on the banking domain. It was something similar. So we took the model, and we did transfer learning on the banking data. So we used the model and its weights, and we allowed the weights to be updated on our banking data. And so these were the stats on how it performed. Our accuracy was 73%. For our training data, we made sure we had equal representation of positive and negative examples. For the test data, we passed in the true distribution of the data points, and most of them were actually positive. And so this was good because we taught our model what it was like to learn positive versus negative conversations. And so if you guys aren't familiar with the accuracy term, here's a confusion matrix. So the way to read this is we have the true label here, we have the predicted label here. And so if the true label is a positive and I predict it's positive, I have a true positive. If the true label is negative and I predict it's negative, that's a true negative. So if I'm in either of those two squares, my classification was correct. But if I'm in either of these two squares, I had an incorrect error. And accuracy doesn't tell me which one I had messed up on. Did I have a lot of false negatives or false positives? And in our example here, we actually care a lot more about false positives than false negatives, because if we predict a conversation to be positive, we're not going to follow up on it. But if we predict it to be negative and we follow up and there's nothing there, we wasted some human time. But there's a trade-off. I can't just predict every conversation's negative, because then I'm wasting a lot of human time. And so that's why, in addition to accuracy, we have this other metric that we're using called false positive rate. And the false positive rate's actually quite low in this case. It's 11%. It's the ratio of our false positives to our true negatives. So it's this square divided by both of those. But we want to make sure we don't start predicting everything's negative. And so that's why we have to balance it out with our false negative rate, which right now is at 32%. So this was the first step in our model. So now we want to improve upon those metrics. And so these are the features to our model. The output from the LSTM model, some conversational features, like user average turn length. We had found that when users were very terse, they actually had much lower satisfaction scores at the end. The agent average turn length, users actually liked it a lot more when the agent had a much longer response. The number of terms that took place, and the duration of the conversation. Did it last 15 minutes or did it last an hour? And then also some temporal features. We wanted to see how day of week and time of day had impacted both the user and the agent. I'm not sure if any of you guys had tried calling customer support late at night. They're generally not all that happy. And then a few other features for kind of our secret sauce here. So we passed all of these features together through an end classifier. First one we had used was logistic regression. It's very interpretable. It actually gives us this probability distribution where I can set my own threshold. If you're less than 50% confident, it's a 1, I want to look into it, or I could set it to be 70% confident. This way we get some prioritization as to which ones we should look at first. And we can see our accuracy is doing better, but our false positive rate had increased over the pure LSTM. So that's why it's important to get all of these metrics to figure out which of the trade-offs are important to you. We'd also tried a random forest, which outperformed all of the other models substantially for accuracy and false positive rate, but we did increase our false negative rate. Because the thing we're trying to optimize for is false positive rate, we're actually OK with this increased false negative rate. It's a little bit more human effort on our end to go through the examples that we had incorrectly flagged as being negative, but that's OK for our problem here. And so this is an example of a random forest. It's a collection of individual decision trees. And so we chose the random forest at the end for the following reasons: lowest false positive rate and highest accuracy. And it also provides pretty good model interpretability. One of the requirements here is we could explain at the end of the day why we predicted it to be positive or negative, what features contributed to the end output. And that was why we actually didn't want to use LSTM as the overall classifier. We can assign a weight to the LSTM output now, but we can't just say this black box thing kind of predicts it's positive, because we don't have that true interpretability. Even though there are libraries to help with that, kind of the more classical machine learning models are a bit more interpretable. And the other reason why we like the random forest is it's part of Spark ML, and we can easily use the Pipeline API with it and switch to Scala. And so on that note, I'm going to hand over to Jamie to talk about how we actually put this into production.
So after Brooke did all of that, well, Brooke and Amir did all of that great work on the notebook side and building the model, we had to figure out how to take that over to production. So when you're taking things out in production, there's definitely a few more requirements and challenges that you have to meet. I'm sure a lot of people in this room are very familiar with that. So first of all, our dev pipeline is mostly Scala and Java based over at FIS Global. We know that a lot of data science is done in Python, and a lot of the natural language processing and deep learning libraries that we use are even Python only sometimes. But we really like having everything in Scala and Java so that we can have everything compilable, and also that's just what our CI/CD pipeline is built for. Next, we needed to be able to close the feedback loop. So no one wants a stale model out in production. We needed to be able to constantly learn on new trained data that's coming into our system. Next, we needed automated deployments. So whenever you're taking anything out in production, you need to have that forethought to think, how are we going to get this out in production in a reproducible way and nice and quick so that ops doesn't have to go and manually deploy everything out in our Databricks cluster or our Databricks account. Then finally, we wanted everything to be streaming. We're building a new data engine over at FIS Global, and one of the requirements that everything is streaming. For this use case in particular, we definitely wanted everything to be streaming because we wanted to be able to follow up quickly on these support chat conversations. So, if someone had a bad conversation, it might not be useful if we see that on our monthly report next month. It might be a little bit too late to follow up at that point. Obviously, there are definitely a few extra challenges that come with doing streaming instead of batch, but we were ready to take those on. So now we have to ask the question, how do we build an architecture that fulfills these requirements, and then how do we get that all out into production? So we have a little architecture diagram for you. It's a bit simplified, but I'll give you a second just to read it, and then we'll walk through it really quickly. Not all that quickly, we have plenty of time. So you'll notice on the very left here, we have our Kinesis Firehose. Cool, laser point. And that Kinesis Firehose endpoint has streaming data coming in from our mobile apps and servers. And we really just get session data, so session ID and maybe some associated data with that session. That data gets dropped into an S3 bucket. As you can tell, we're AWS-based. That S3 bucket acts as a source for our Spark streaming job that's running in our Databricks account. Once we have that into our Spark streaming job, we don't have the full conversation yet. We need to go against a third-party service that helps us with our support chat, give it the session info, and then it will return us the full conversation of that support chat. Once we have the full conversation, our Spark streaming job can go over here to this model bucket, read in a model, apply that model, enrich our data with all of this new sentiment and conversational analytics data, and then we can finally write that into our data lake. So you might notice we've checked one of our requirements. We are streaming, check. So for another requirement, we wanted to close the feedback loop, right? So you'll notice at the bottom of this diagram, we have a second Spark job. This time it's a batch job, and that batch job can grab, on a regular basis, any labeled data that comes into our data lake, train on that new data, and then append the model in our model bucket. And we can really update it with the new information that we've learned on that new data. It doesn't have to replace that model. So as you can see, we've closed our feedback loop. We have a nice little loop here. And that's another check for another requirement. We have a constantly learning model, and it's streaming. But there is one that was definitely going to be a problem from the start, and you might see where we're going with the languages. So we wanted everything to be in Scala or Java, right? But a lot of the processing that we did and a lot of the work that was done in the notebook was in Python. So how do we deal with that? And so it was really not too complicated. Spark is really great. We can train in Python, save the model to our bucket, and then we can apply that model in Scala. But not quite that simple. You might notice that, you might remember from Brooke's part of the talk, we used the Keras model, and that doesn't have an implementation in Scala. So how did we get around that? How did we apply a Keras model in our Scala-based streaming job? So we're just going to, you'll notice in this next slide, we're going to zoom in on what's happening in this Spark streaming job. So what we can do is we can train in Python, like I said, but when we save the model out, and what's happening in our Spark streaming job is you can call a PySpark file in your Scala code. That PySpark file will register a UDF with Spark, and that UDF will apply the Keras model to our data set. So we can load in we can register that UDF, and then once we have that UDF registered, we can apply that UDF using Scala in our Scala code. And thus, we've jumped our language hurdle. And you can see that it's really not an issue of Python versus Scala. It's an issue of making Python and Scala work together and having the data scientists and the data engineers all happy and work in harmony. So another requirement, check. We've solved our language problem. So you might remember there's one last requirement. We needed to be able to deploy everything in an automated fashion into production. So how did we do that? First of all, another little diagram here, and this is how more or less our CI/CD pipeline works. We have infrastructure as code. So we have all of our infrastructure defined in a file. Jenkins will read in that file. Jenkins is a build server. It'll build all our code, build our packages, send that off to Rundeck. Rundeck is just a tool for doing operations automation. And that Rundeck server will run an application that we've developed in-house that we use as our deployment manager. That deployment manager will leverage Terraform to deploy our AWS infrastructure. And Databricks conveniently offers a wide array of APIs, so we leverage the job API to be able to deploy any Databricks infrastructure that we need to deploy that works with our AWS infrastructure. So another requirement check. We have our automated deployments, and everything's great. And just to recap, we've built our streaming architecture that constantly learns and is easily deployable. So you might be asking me, unfortunately I don't have a slide for this, but you might be asking me, that's great, we have everything in production, we have all of our enriched data into our data lake, but how do we actually affect our customers' happiness? Well, once we have all of our data in our data lake, really that's the key. The possibilities are endless from there. So once we have everything in our data lake, we can choose our BI layer of choice, read in all of our data, visualize it, slice and dice it how we like, see what's going on with our conversation. Do people like shorter conversations, shorter responses? And we can take actions to try and improve this, and then go back and see how that worked. And since we've been measuring the happiness of our users in those conversations, and really get a sense of the quality of those conversations. So quick recap of the entire talk. We had this great idea around conversational analytics, and we knew that we wanted to do it and that we needed to do it for our clients. We turned to Databricks. Databricks was able to mock up a lot of the work and built these great models for conversational analytics. We were able to take those notebooks, productionize them, and then we were able to make our customers happy. And isn't that, in the end, our goal? So we want to thank everyone for coming to our talk. And we're really excited to be up here. And finally, we want to give a shout out to Kevin Malat and Aaron Colcord, who are doing another talk, Life is But a Stream. We really encourage you to go to that talk, especially if you want to learn more about the streaming aspect of this talk. They'll really go deep into that. and that's at 3:30 p.m. Thursday, so tomorrow, in the streaming track room, room 2007. So now we'll open the floor for questions, if there are any questions.
Yeah.
Yeah, please use the mic if you can.
If not, just speak loudly. We'll repeat it for everybody else.
Yeah.
I'm just curious about transfer learning. How big was the data? How do you go about getting the data set? Can you talk about the size of that data set?
Yeah, so the question was about transfer learning and the size of the data set. So the data set that we had found that was openly available was on the order of a few gigabytes. Our internal labeled data set was not all that large. It wasn't larger than 1 gigabyte worth of labeled data. And so that was why we had done the transfer learning. It's because we were able to find a much larger open source data set, and we could initialize our model weights from that and then apply it to our smaller data set. Who labeled the data for us? This was from some prototypes with some customer conversations where we would ask for the labels to come actually from the agent to label the conversation.
Did your data have any aspects associated with that? Like aspect-oriented sentiment? Like this one was great, but the data was bad? Those kind of things?
Like, this one was great, but what was bad?
Something like the food was bad, but the restaurant was great. Aspects in the sentiment.
Okay, so the question was about aspects in the sentiment. Something was great, but something wasn't bad. That wasn't something that we had investigated. We were simply just trying to do positive, negative. That's definitely an area where we could follow up on. And also, like, topic analysis is one of them. Like, what are most of the customers complaining about, for example? Or what are the things that the customers love?
You mentioned you wrote the UDFs in Python and then in convert the Raptor objects to Scala. So can you explain how easy it is and
Yeah, actually, we can show you that inside of a notebook if you want. So in here, when I said define UDFs, it's actually very easy to define them. All you have to do is you define your function you want to run, and then you do spark UDF register. This is the name which I can then access from Scala. You'll have to use it using like a select expression, so kind of like from the SQL API, but now I can use this in Scala. I just say, this is the function I want to pass in. This is what I'm going to make it available as inside the SQL namespace, and then this is the return type. Sorry, can you say that again?
Well, the Scala API is a lot faster, first of all, and then, like we said before in the slides, we like having Scala. It works well with our CI/CD pipeline.
Everything that we had done from the model building side could have been done from pure Python, except for Stanford CoreNLP. That one does not have a Python wrapper. But actually, that didn't affect the end model, so yeah, everything could have been done with Python. So the question was, what would be the performance penalty of using pure Python? In this case, the performance penalty would mainly come from this section from Approach v1, where we're creating custom functions. UDFs in Python aren't as fast as Scala UDFs. With Approach v2, we actually were able to leverage primarily built-in functions from Spark. And whenever we can do that, it's actually about the same performance between Python and Scala. But it was more to fit into the overall dev pipeline. We can't bundle up our Python code into a jar file. So
when you're writing a sentiment, for misspellings and such, are you taking them all as tokenized elements, or was there a dictionary that was burning down the completely misspelled words?
So the question was about misspelled words. We had looked at an autocorrect library, actually. There's one available from Python. Didn't do all that well, and it actually had changed some of the words that were correct, but not in the domain it was trained on. So we just tokenized them. We had our own tokenizer set up to do some of that tokenizing. With Approach v1, this automatically did it for us. We didn't have to do any of the pre-processing. We could just apply them out of the box. Yeah. Either of you.
When you define a UDF like this, I assume that for inference for your LSTM, you probably use like some serialized version of the Keras model or something. Are there any difficulties with taking a serialized pickle file or something that Python can understand and importing that over into Scala?
Actually, not really, especially if you use MLflow to load in the model, because MLflow both has the Python and the Scala client. It actually makes it very simple to do. Yeah, you just give it the path to the model, and then it can load it in just fine.
Can you talk a little bit more about how you actually use the information to make customers happy? Like, that's a little bit unclear to me. So, was it just scalable reporting to leadership and benchmarks, not, or
So what I can so we have a BI tool that sits on top of our data lake that we call Metrics Intelligence, and we have dashboards that we can use to display that data and present it in a useful way to decision makers.
just a follow-up question, was there like any kind of feedback loop to kind of give, let's say, feedback to agents, kind of change how they maybe interact with customers, or is it like later on?
So let's just repeat the question.
Yeah.
The
Oh, yeah,
question was,
sorry.
is there any feedback loop about how to potentially change the agent's behavior if we can identify one of the agents consistently gets lower scores than others? Right now, this hasn't, we haven't built in that functionality, but that is something that we want to do.
Yeah.
Is the only channel mobile apps and the online chat, or was there integration with phone calls and voice, text, anything on those accounts?
So the question is, are we only focusing on mobile chat, or are we integrating with phone calls and such? The answer is we're currently just focusing on the mobile chat, and we're looking at all of those other use cases. Also, all the other use cases with conversational banking that I mentioned in the earlier slides.
And actually, I just want to follow up on that answer for a second. That's actually a very interesting question because how you handle spoken language and how you handle written language is actually quite different. You don't have all of the us with the textual language, so simply scribing it out might actually yield different model performance. So we haven't gotten to that stage, but we are going to look into whether or not we'd actually need a different pre-processing step first.
The question was, in your experience, what's the percentage these days actually phone call versus mobile? So what's it justify investment on these grounds on the scale with just the mobile app?
Kevin or Aaron, would you know about that?
Did it justify the investment in going this way? Or is that the core question?
To justify the balance between the actual phone call conversation versus the mobile app.
Well, where I go is basically that there's a lot more right now there was a study that came out a couple days ago that showed that by 2021 conversational banking will outpace mobile. So this was really our direction, which is how do you really enable the self-learning type of conversational system that would be, leading edge in 2021. So that's where I'd say that where we're looking at it. Whereas if you just think about it, I mean, almost everybody in this room, if you think about the times you've gone to your last bank account or last time you even called your bank, or even the time that your bank actually spent the time to even pick up the phone, right?
This
Because
is us in the Silicon Valley. Midwest, the East Coast.
we're from the Midwest, so they don't pick up the phone there either.
Yeah, so I just wanted to say that a little bit louder since I'm not sure if everybody could hear Aaron. He had said there was a study that came out a few days ago that by 2021, conversational banking will outpace traditional banking and phone calls.
I think
Okay.
we're over time.
Yeah, so we're over time. Feel free to find us at the conference. You can also find Amir, who's in the back over there in the Databricks shirt, also Kevin and Aaron, and their talk tomorrow, 3:30. Thank you.